our focus right now is on how can we determine the order of reaction for a given chemical in a chemical reaction. The order of reaction, once again, would be the exponent in a rate law expression such as this one, where we have rates equal to the rate constant times the concentration of chemical A raised to some exponent which we refer to as the order of reaction with respect to chemical A. And we have several means of determining what this exponent or the order of reaction is with respect to chemical A. One technique is to use concentration and rate data. This strategy would involve using the equation where we have our rate of trial number 2 over the rate of trial 1 is equal to the concentration of our chemical in question in trial 2, our concentration of the chemical in question in trial 1, and then this is all raised to the m power. The m power, when we solve for this, would give us the order of the reaction with respect to chemical A. The second strategy is we can use a graphical analysis of data to determine the order of reaction with respect to chemical A. In the graphical analysis technique, we're going to match up several equations with our familiar equation of y equals mx plus b. The equations are, we have one with concentration of chemical A, one where we plot natural log of the concentration of A, and one where it's 1 over the concentration of chemical A. In working with this graphical technique, what we do is collect data where we measure the concentration of chemical A at specific moments in time as the reaction proceeds. Plotting the data and seeing which plot provides us with the most linear relationship tells us the order of the reaction with respect to that chemical. Now, one thing before we proceed any further is to make clear that in this particular strategy, that the previous strategy where we compare rates and concentrations, that's going to be our apples, and the graphical analysis is oranges. And we have to make sure that we keep our apples and oranges separate from one another. These are two separate and entirely distinct strategies for figuring out the order of a reaction with respect to a chemical. The video right now, we're going to focus on how to use the graphical analysis of data to determine the order of a reaction with respect to a specific chemical. Here's how the graphical analysis would work to allow us to determine the order of a reaction. We have our rate expression, in this case for zero order, rate equals Ka raised to the 0 power. We have our equation, which we match up with y equals mx plus b. Now, if we make a plot where our y-axis is the concentration of A and our x-axis is T, if this comes out to be something that is linear, that would tell us that the order of a reaction with respect to chemical A would be 0 order. The nature of the data is that this A sub naught represents our concentration of A at time equals 0. The A over here represents the concentration of A after some time t has passed. So if we can measure the concentration of our chemical as the reaction proceeds and say that after 30 seconds we know the concentration of A is 0.50 molar, we could put that data into this equation. If we do this over a series of time, where we find the concentration at 10 seconds, 20 seconds, 30 seconds, 40 seconds, we can now plot the concentration on our y-axis, plot the time on our x-axis, and if this proves to be a linear plot, what that tells us is the reaction would be 0 order with respect to chemical A. If we take the same data and plot it where our plot would now be the natural log of A versus time, if this plot were to come out linear, it would tell us that the reaction is first order with respect to chemical A. If we now plot the data in a third manner, where we plot it with 1 over A, concentration of A versus T, if this plot were to come out to be linear, it would tell us that the reaction is second order with respect to chemical A. In the lab exercise, what we're going to do is collect the data, and we're going to make one of each of these graphs, concentration of A versus time, natural log of concentration of A versus time, and 1 over concentration of A versus time. Whichever plot comes out linear will then tell us what the order of reaction is with respect to chemical A. If the A versus T plot comes out linear, that tells us the reaction is 0 order. If the natural log of A versus T plot comes out to be linear, that would tell us then that the reaction is 1st order with respect to chemical A. And then the third plot we'll do will be 1 over the concentration of chemical A versus time. If this plot were to be the one that proves to be linear, what that tells us is then the reaction is 2nd order with respect to chemical A. When we make these 3 plots, whichever one of the 3 plots comes out to be most linear, that then tells us what the order of reaction is with respect to that chemical, whether it's going to be 0 order, 1st order, or 2nd order. Depends on which plot comes out to be the linear relationship when we plot our data. For example, let's say that we plot some data and we make our plot, one of them's concentration of A versus T, one of them's natural log of A versus T, and the third is 1 over A versus T. We notice in our plots that the natural log of A versus T graph came out to be linear. What this tells us when this graph came out to be linear is that the 0 order is not correct for this particular reaction because that's a curved plot for concentration versus time. And the 2nd order is not correct because our 1 over concentration did not provide a linear plot. But when we see our plot of the natural log of concentration versus time, that would tell us that with respect to chemical A, this is a 1st order reaction based on what this plot tells us by virtue of plotting with a linear relationship. Another piece of information we can gather from these graphical plots, again, if we compare to our y equals mx plus b relationship, we can see if we make our y-axis, each of these items, and our x-axis is time, then our value of m, which is the slope, can give us the rate constant in each of these plots. For example, let's say we find that our plot of concentration of A versus time, which would tell us the reaction is 0 order, we can see from our relationship here that m, or the slope, is equal to negative k. Therefore, if we just take the opposite of the slope, negative slope would give us the value of the rate constant for this particular rate law expression for the 0 order reaction. Similarly, for the 1st order reaction, if we got a linear plot for the natural log of A versus time, we can see again over here that our negative k and slope equal each other. So in our 1st order relationship, we also have the scenario where the negative or opposite of our slope will give us the rate constant for our rate law expression. For the 2nd order rate law expression, the slope k, because this plot gives us a slope that has a positive value, in this case, the slope of the line gives us our k value for our rate law expression if the graphical analysis indicates that our rate law, we have a 2nd order reaction with respect to chemical A.